Quiz 7, which is related to chemical energetics topic. The first question, the Born-Haber cycle can be used to determine the lattice energy of a magnesium chloride. Different values are given. The diagram shows an incomplete Born-Haber cycle for the formation of a magnesium chloride from magnesium and chlorine. Complete the diagram. So what will happen, like elements will form the ions and then ions will form a compound, is same as element directly form the compound. So if you want to complete, the product will be, we want a magnesium chloride, so product will be MgCl2 in a solid state. So first, we atomize magnesium, we produce a magnesium atom, like convert magnesium solid into magnesium atom, like gaseous state. Then or it can be together, like because the numbers of the arrows, this is a formation is there, because when elements are forming a compound formation, when ions are forming a compound, that is a lattice energy. So first we will atomize them, then we will ionize, and then it will be the affinity. Now we'll check what are the values given. So enthalpy change of atomization of magnesium is given. First ionization of magnesium, second ionization, enthalpy change of atomization of half mole of a chlorine is given. Then first electron affinity is also given. Then enthalpy change of formation of magnesium chloride. And from that, we have to first complete the diagram by writing a formula of the correct species. Include the state symbols on the 5 empty horizontal lines. So first, we can atomize magnesium, then we can atomize chlorine, then we can ionize, like first ionization of a magnesium and then second ionization of a magnesium, and then electron will be added. Electron affinity, the arrows are pointing up. If they're endothermic, they're pointing up. If they're exothermic, pointing down. So first we atomize magnesium. So it will become magnesium atom in a gaseous state. Then we can atomize chlorine as well, like converting a chlorine atom, chlorine molecule into chlorine atom. So, but it will be twice. So this will produce, magnesium is already gas, and it will produce 2 chlorine atoms in a gaseous state. Then we will remove the electron from magnesium. First electron will be removed. So magnesium will become +1 in a gaseous state. And then chlorine, 2 chlorine in a gas. And then we remove the second electron from magnesium. So magnesium +2. There will be 2 electron and plus 2 chlorine out there. And these two electrons, each chlorine gain 1 electron. So 2 chlorine atoms gain 2 electron and form 2 chloride ion. So we have magnesium ion and chloride ion. And here it will be a product MgCl2. Now in terms of values, if we write and identifying the start where the 2 arrows are pointing out, that is a start of the cycle. So here the 2 arrows are pointing out, so that is a start of the cycle. Here the 2 arrows are pointing in, that is the end of the cycle. So if we follow route 1 or we follow route 2, the overall energy change is independent of the route or the path we follow. So first one, atomization is 147. So atomization of a magnesium 147. So we write here 147.7. This is an atomization of magnesium. This one 147.7. Then this is atomization of a chlorine, but how many chlorine atoms are produced? Two chlorine atoms. So if you want to produce one chlorine atom, for one chlorine atom, the atomization, like because half chlorine molecule means one chlorine atom, atomization is 121.7. But because there are two, so the atomization will be twice. So this will be 2 multiplied by 121. It was 121.7. So this will be 2 multiplied by 121.7 because two chlorine atoms are produced. If you produce one chlorine atom, then we remove the first electron from magnesium, and we remove the first electron from magnesium. To remove the first electron, 738. Second electron, 1451. First ionization, second ionization. So 738, 1451. So this will be first electron is removed, so 738, 1451. Here what happened? Two chlorine atom gain two electrons. So one gain one. So that is called affinity. When electron is added to neutral gaseous atom, that is affinity. So electron affinity, first electron, when one electron is added to chlorine atom, it is minus 348.8. So this energy is minus 348.8 negative, but it will be multiplied by 2. Why? Because for one chlorine, when one electron is added, it is 348.8. If two are there, it will be multiplied by 4. And this will be the lattice energy which we are finding. And what about the formation is given when magnesium and chlorine react to form magnesium chloride? So this is minus 641. So this will be negative 641. Now what we have to do, we identify where the two arrows are pointing out, that is the start of the cycle, and where the two arrows are pointing in, that is the end of the cycle. So if we follow route 1, like if we write in terms of equation, if we add 147.7 plus now we just have to substitute the values, plus this one 2 into 121.7, then plus 738, then plus 1451, and then plus this value, which is negative 348.8 multiplied by 2, because this value plus the lattice energy is equals to this formation, because like overall energy of this route will be equals to energy of this route, and the energy of this route is minus 641. So we just, lattice energy is our subject, so we just work out the lattice energy, which will be around 2000 negative 2520. Lattice energy should be negative because when ions form a compound, like it's a bond formation, so it must be negative. Is it clear? The Born-Haber cycle. So whenever you need a lattice energy from here, you will have an element in a Born-Haber cycle. Here you will have ions, and here you will have a compound. So first element atomize, then ionize, and then affinity. It will form ions. Ions form the compound. The same as the element directly form the compound. So this will be the start of the cycle, and this will be the end of the cycle. The compound hydrogen, which is N2H4, is a liquid, is used as a rocket fuel, and it reacts with oxygen to form nitrogen and water. Complete the Hess cycle and use the data in the table. Calculate the enthalpy change of oxidation of this reaction. So this is what we need. We have formations are there. If formations are there, what is the link you will add? You will add a link element. If combustion if combustion is there, you will add a combustion product. So, and like element form a, if formation is given element to reactant, you will draw an arrow, and element to product, you will draw an arrow. If a combustion product, both will point downward. What are the elements here? We have a nitrogen, which is a gas at room temperature. We have a hydrogen, which is also a gas, but how many we need? 4 of them. So it will be 2 molecules of hydrogen, and we need O2, so oxygen gas. Here, 1 mole of hydrogen is formed, so it will be 50 plus 50.6. Here, nitrogen is not, water is formed, but how many moles? 2 moles. For 1 mole, it is minus 285.8. So multiplied by 2. Now, the 2 arrows are pointing out. So this is the start of the cycle. 2 arrows are pointing in. That is the end of the cycle. So if we follow route 1 or we follow route 2, the overall energy change is independent of the route or the path we follow. So it will be 50.6 plus the enthalpy change of this reaction equals to minus 285.8 times 2. So if you need enthalpy change of this reaction, so it will be minus 285.8 multiplied by 2, and this is minus 50.6. So that will be the enthalpy change of this reaction. So whenever elements are given, like formation is given, you will draw an arrow from element to reactant and element to product. But if it was a combustion was given, then you will draw arrow from reactant to the combustion product and element product from product to a combustion product. So this enthalpy change will be minus 622 kilojoule per mole. Some bond enthalpies are given in the table. So calculate the enthalpy change for oxidation using a bond enthalpy. So you have to use the bond breaking side. The structure of hydrogen is N2H4. And now we should write the oxygen in the reactant there as well. You have to write the oxygen like in the element you mean. Yes, you have to write, because nitrogen, hydrogen, and oxygen, these are the elements which react. So you have to mention those elements as well. So here, nitrogen double bond is there, because the structure of hydrogen is N double bonded with N, and then sorry, and not double bond, it will be single bond, because it is nitrogen can form 3 bonds. So this will be N. So this will be nitrogen single bond is there, and there will be 4 NH bonds. And oxygen double bond, that will be the bond breaking side. And bond forming side, nitrogen triple bond, and then H2O is there, so HOH. So how many? 4, because in one water molecule there are 2 OH bonds. So in 2 water molecules there will be 4 OH bonds. You just have to substitute bond break, like this will be 158 NH bond is 391, and oxygen double bonded with oxygen 498. And bond forming nitrogen nitrogen triple bond 945, and 4 HO or OH bond 464. So to get the enthalpy, to find the enthalpy change, it is a bond breaking minus bond forming. Just take a difference, and you will get the difference in the two values, which is around minus 58, 581 kilojoule per mole. But practically, when we use a bond enthalpy and the Hess law, we won't get the same answer. What is the reason? You have to memorize. One thing, like these all bond energies are based on the gaseous substance. Like these values of the bond enthalpies are always in a gaseous. Like what does it mean? It means when we break the bond of nitrogen in a gaseous state. We break even in this hydrogen is liquid here, but all the bond enthalpies, like the bond enthalpies are given when we have the substance in a gaseous state. Like we are breaking the bond when the substance is in a gaseous state. But here we have a liquid state, water also in a liquid state. So to break the water HO or OH bond in a gaseous state, we need this much energy. But if the water is there in a liquid state, we need a different energy. So one reason that why whenever we calculate the enthalpy change using a bond enthalpy, why we won't get the same answer as Hess law? Because the bond enthalpies are always based on the gaseous substance. Like substance should be in a gaseous state. And another thing, these values are average energies. Because in reality, what will happen in practical, like according to the values, the OH bond energy is given. The OH bond energy is given 464. So means it shows that 464 is needed for this bond and 464 is needed for the other bond. But in practical, it is not correct. This is the average energy. Average energy is given. Actually, what happened, to break the first bond, we need more energy. But when we break the first bond, to break the second bond, we need less energy. So maybe to break the first bond, we might need 600 joules. To break the second bond, we may need like 280 joules. So the average value is always given. So bond enthalpies are always the average energy needed, not the actual energy. Because in actual, the energy required to break the first bond, even identical bonds we are breaking, say we are breaking a bond in water molecule. When I try to break the first bond, because water molecule is stable, so I need relatively more energy. But when the first bond is broken, now it is unstable. To break the second bond, we need less energy. But you can see for all the OH bond, the energy is given 464. So which is an average energy need to break these bonds. So bond enthalpies are always the average energies to break the bond. In question 3, ammonium nitrate is used to manufacture fertilizers and explosives. The first two reactions in stage 1 involve the production of hydrogen. At temperature T1, the methane reacts with excess of steam to give hydrogen. At a different temperature, the carbon monoxide reacts with more steam. Give a reason why excess of a steam is used in the first reaction. So when we use an excess of a steam, what will happen? It means we'll have more reactants, so equilibrium will shift towards the right hand side. So as a result, it will produce more carbon monoxide, because shifting of equilibrium depends on temperature, pressure, and concentration. So why we use excess of a water molecule, steam here? So like more than enough. So for a first reaction, when we use excess of, first thing, steam is reacting in, like it's a reactant of both. Like For both reactions, it is reacting. And another thing is that as a result, what will happen when a steam is reacting, it will shift the like more reactant, so it will shift the equilibrium towards right, or it will increase the amount of hydrogen. Predict at which temperature, predict which T1 or T2 is a higher temperature and justify your answer. Look, this reacts, both reactions are, this is endothermic and this is exothermic. If we want to shift the equilibrium toward the right hand side or to get more product, endothermic reaction prefer high temperature, increase in temperature, so that the equilibrium shift toward right. But for exothermic reaction, if you want to shift the equilibrium towards the right hand side, so it prefers low temperature. So this T2 should be less and T1 should be greater. And you can also mention, because the forward reaction is endothermic. Devise the overall equation for a production of hydrogen stage 1. State symbols are not required. We need an overall equation. So how to work out the overall equation? What we simply do, we can add the two equations. If I add the two equations, carbon monoxide will cancel with carbon monoxide. So we are left with CH4. This is the answer for the other part. Then H2H2, this will give 2H2O. This will give 4 hydrogen and plus CO2. So this will be the overall equation for this reaction. Then suggest one reason why carbon dioxide is the third reaction in stage 1 involve the removal of carbon dioxide using aqueous solution of N-methyl and diethylamine. In part 3, we need the combined equation. So that overall equation. So if we need the overall equation, what we have to do, we just have to add the two equations which are given. So these are the two equations which are given. So what we have to do, we have to add them. When we add, carbon monoxide is on the reactant and here, and the other side product. So this will cancel out. CH4 is left, nothing to cancel out with CH4. H2 and H2O, they are on the same side. So we add them. H2 and 3H2 gives 4H2. And this is cancelled. So we are left with carbon dioxide. So this is the overall equation. So we have to add the two equations. Then the third reaction in stage 1 involves the removal of carbon dioxide using aqueous. So what is the reason for removing carbon dioxide? So you can refer the effect of the carbon dioxide to the atmosphere. Like it is a greenhouse gas, so emission to the atmosphere may leads to a global warming. You can mention that. Name the type of a reaction occurring. You see more reactant and only one product. So if we have many reactant and they form one product, so what we call this type of reaction. And another thing, you can also compare the nature of the reactants. Like the compound of nitrogen are alkaline, like ammonia, amine, these are alkalines. What is the carbon dioxide? It is an acidic oxide. So you can also refer neutralization. Why we did not say addition reaction? Because the arrow, it was not in one direction, it was reversible. That's why we can say addition, but why addition is not acceptable here? as the arrow is multiple, like pointing reactant and product. So reactant can form a product, product can form back the reactant. If the arrow was pointing only in one direction, then only we can say it is addition. Then we have to draw a displayed formula. Displayed formula means like we show all the bonds and all the atoms. So CH3 is there. Then nitrogen. Then next to that is CH2, CH2, OH, and how many of them? Two of them. So with nitrogen, CH2, CH2, OH. And same thing, another CH2, CH2, and OH. In stage 2, the hydrogen from stage 1 react with the nitrogen from air to produce ammonia. The reaction condition give one advantage of using a pressure of 200. If we use a very high pressure, here we have 4 moles and here we have 2 moles. So where the balance will shift, the equilibrium will shift towards the right hand side. So as a result, equilibrium shift towards the right hand side. So what we will get a higher yield of ammonia. But another disadvantage is that because to produce this very high pressure, we need more energy. So it will increase the cost or make the reaction expensive. So high pressure increases the cost and make the reaction expensive. That's why we should prefer to use a low pressure. The reaction in stage 2 has an activation energy of 70 kilojoule per mole. The uncatalyzed reaction between nitrogen and hydrogen has activation energy of 290. Complete the energy profile diagram. Label the activation energy, enthalpy change, and you must match the scale as shown from production. So first we have to label this scale like x-axis and 70 kilojoule is the stage 2 has an activation energy with a catalyst 70 and uncatalyzed is 290. Like if we take this 70 or 100, 200, 300 above this will be like idea. So this is with catalyst it is 70. But without catalyst it is 100, 200, so 290 it will be somewhat here. So this one is this one is 70 and this one will be around 290. But because the axis is given, so you will mark the axis and it should appear that it is correct. And then enthalpy change, this will be the delta H. Either the scale you mark or it should appear that the proportion is same, like 70 to 290. Suggests why use of a catalyst makes stage 2 more sustainable. So if you use a catalyst, what is the advantage of using a catalyst here? So it will increase the rate of a reaction. So as it increases the rate of a reaction, we need less energy because sustainable reaction means like can be done or carried out with a low energy. So if you use a catalyst, rate of a reaction will be higher and it reduces the cost. Then in stage 3, nitrogen monoxide is produced. Give one reason why a high temperature is needed for this reaction. look, some of the compounds, their nature is inert. Like example, nitrogen. The nitrogen reaction usually start at around 450. So some of the reactants, their nature is inert or they are not reactive. So, or some of the reactions, they have a very high activation energy. So even though that this reaction, as you can see, the forward reaction is exothermic. So exothermic reaction, to shift the equilibrium towards the right hand side, they prefer low temperature. But even for this reaction, why we use a high temperature? So what is the reason for using a high temperature? They might have a high activation energy or inertness, or the strength of the bond in nitrogen, like nitrogen hydrogen bond or oxygen oxygen bond. You can also refer that as well, like need more energy to break down. Suggests why only small amount of energy is used to obtain a small amount of energy is used to maintain the temperature of. So why we don't need too much energy to maintain 1100 Kelvin? You can see the forward reaction is exothermic. So when the reaction occur, the reaction is exothermic, so it releases energy. As it releases energy, that energy will be used to maintain the temperature of 1100 Kelvin. So we don't have to provide enough energy. It's the same idea like combustion. In a combustion, even combustion is exothermic, but to start up, we have to provide an activation energy. But when a combustion happen, it release energy, so it will reach activation easily. NO from the first reaction, stage 3 is cooled and then converted into nitrogen dioxide and nitric acid. Explain how adding a water in the second reaction affect the yield of nitrogen dioxide in the first reaction. If we adding a water, so if we add water, water will react with nitrogen dioxide. If water will react with nitrogen dioxide, so amount of nitrogen dioxide in the first reaction will decrease. If the amount of nitrogen dioxide in the first reaction will decrease, so where the equilibrium will shift, the equilibrium will shift towards the right hand side. So as a result, we'll get more. So nitrogen dioxide, which is produced, react with water. So amount of nitrogen dioxide decreases. So this will shift the equilibrium towards the right hand side. Complete the enthalpy diagram. Here we have enthalpy change of formations are given. So formation for ammonia, nitric acid. So when formation is given, here element is there. So here we have nitrogen and nitric acid, like ammonia and nitric acid. First, it is, as you can see, different values. When nitric acid is aqueous, it will be -32, and when ammonium nitrate is aqueous, it is 25.6, like the dissolve. This is given for gas, liquid, and solid. So here we'll have ammonia and nitric acid. Ammonia will be gas and it will be liquid, NH3 and HNO3. How we identify? Because if you see, when nitric acid is the first one, 200, and there's a formation of ammonia and nitric acid, then nitric acid dissolve, then this is what we need here. This is the formation of ammonium nitrate. Ammonium nitrate formation is how much? Ammonium nitrate formation is -365.6. So 365.6. And this is a ammonium nitrate dissolve. So how much is dissolving for ammonium nitrate when it dissolves? 25. So this will be 25. Now, how to start a cycle? Where the two arrows are pointing in, that is the end of the cycle. Where the two arrows are pointing out, that is a start of cycle. So if you follow route 1, like you follow this route or you follow route 2, the overall energy change is independent of the route. So it will be minus 220 minus, like actually it's addition, like plus into minus 32.6 plus the enthalpy change of a reaction equals to the root 2, like minus 365.6 plus 25. And this is your subject, so you just work out the enthalpy change of this reaction. Suggests reason why it is more profitable to carry out all 4 stages in the same site instead of using different sites in different industrial ammonium sulfate. Like if you want to produce ammonium sulfate, all must be carried out at the same site. What is the advantage of doing that? First thing, because if different sites are there, one site you're preparing hydrogen, another site you're preparing ammonia, other side you're preparing nitrogen dioxide. So you have to transport all of them at one place. So transportation costs, it will minimize the transportation or reduce the transportation cost as well. That is one thing. And the second thing, like what might happen, like the energy, like example, if it energy is released in one process, we can utilize that energy for the second process. If we are producing them in different sites, so what might happen, that the energy which we use for the first one, we cannot use for the second one, as it will be either lost or to the surrounding. And operational cost will also be minimized. If we use them at one site, it will minimize the operational cost as well. Is it clear? The pop quiz, which was related to chemical energetics.